Morning, everybody. Hope everybody had a good Mardi Gras break. Won't be long before we're at spring break, so you all have spring break and mini spring break. So that's good. All right, so today we're going to finish chapter 5. Let's do a quick review of what we were talking about last time we met for class, and we were talking about addition reactions to alkenes, and we talked primarily about the addition of HX, HCl, HBr, HI, and water across a carbon-carbon double bond. So for example, we can use HBr, and we have the possibility, anyway, of generating two bromides, but only one actually forms. Which one is it? The first one, yeah. This is the only thing that forms in this particular reaction, not this one. All right, even though you could imagine it adding both ways. So, whose rule is this? Yeah, this is Markovnikov's rule. And Markovnikov's a lot to spell, so I just say Mark. Okay? So Markovnikov's rule dictates which product we have. What does Markovnikov's rule actually say? If you were in your study group explaining it to your friend who had forgotten, how would you explain it? Repeat that, please.
Parts of the molecule that with the most hydrogens.
That's right. So the carbon of the alkene, you've got two carbons, right? The carbon that has the most hydrogens, which is this one, is going to get the hydrogen. That's what Markovnikov's rule states. Okay, and so that holds pretty well here, and you end up with this bromide. Okay? We can also add water across the carbon-carbon double bond. If I place an alkene in water, will this just happen by itself, or do I need something else? I need something else. What else is that something? I need some kind of acid, right? And usually what we use is sulfuric acid. So we need a little bit of sulfuric acid. And I'm just going to write cat in there for catalytic. We just need a small amount, right? What's the functional group going to be when we add water across a carbon-carbon double bond? It's going to be an alcohol. And in this particular case, I'm going to create this alcohol, which we call a Markovnikov alcohol because it goes through a Markovnikov addition. By the way, this is isopropanol. This is your rubbing alcohol. This is one way in which they actually make this. You can get propene from natural gas and petroleum sources. You can take sulfuric acid and water. They may use a different catalyst, I don't know, industrially. And that's how you make rubbing alcohol, is to hydrate the alkene. That's one way in which you can make it. Notice I've written these reactions as if they went to completion. Why did I do that? Why am I not showing these as equilibria?
Because it really rarely goes the other direction, so we say it doesn't exist.
Okay, you're on the right track. I can actually make it go in the reverse. I can, but I have to use different reagents to do that. So technically it is reversible. But it doesn't reverse here. You're exactly right. Why is that? Essentially it all goes to product. Why? In both cases, why is the product so much favored that we just draw one arrow? Pardon? Sigma bonds, that's right. We are sacrificing a weak pi bond and we are gaining strong sigma bonds. The reaction will lie to the product side. It's all about stability, right? And so we learned about this idea of adding things across a carbon-carbon double bond. So let's look at the mechanism for just this one. What do I mean by mechanism? What is a mechanism? Is what I just drew up there before a mechanism? No, that's just reactants giving products, right? But you don't know how it happened. You just memorized that, right? If I take this alkene and HBr, I'm going to get an alkyl bromide. But there's steps involved to that. What do you suppose the first step is? If I take propene and I put it in the presence of HBr gas, what do you think the first step of that reaction is going to be? I can break the pi bond. Why would I break the pi bond first?
Because we want it to be a sigma.
We do want it to be a sigma bond, but we don't really want it to be a sigma bond. We just know that that's the result.
Because
Why would the pi bond want to break? That's a better question.
to create two sigma bonds for the hydrogen.
Okay, and that explains why it goes complete to completion. That's not a wrong statement, but it doesn't tell me why we're going to break that pi bond in the first step. It's weak. It's weak. It's the weakest of the bonds. Right, remember the pi bond just touches on the side, those p orbitals, they're pretty weak. The electrons are above and below the plane of the atoms. They're accessible. Okay? And so we're going to break that pi bond, and we're going to draw an arrow from the pi bond to where? Top. To the top. Southern Miss. Right? Where am I going to draw it to? Am I going to draw it to the bromine, or am I going to draw it to the hydrogen? Bromine? Okay, let's think about that. If I take this pair of electrons and I go towards the bromine, does that make sense? And since I'm questioning it, you're probably thinking no, but you don't know why, right? Why doesn't that make sense?
Hydrogen has a +1 charge, so it can.
Close. You're close. Does it have a +1 charge? No, but it's a polar bond, isn't it? And so it has a partial positive charge, right? And bromine, being electronegative and being far down on the, it's pulling electrons to itself. It has a partial negative charge. And in fact, bromine also has lone pairs of electrons around it, right? So if I'm a pair of electrons, am I going to want to go to the side of the molecule that's got all these lone pairs? What'd you learn in Gen Chem about lone pairs? What do they like to do with each other? They like to repel. Remember your Vesper theory, valence shell electron pair repulsion? That led to different things. So this actually isn't going to happen. Okay? The electrons are actually going to go to the hydrogen. And the electrons between the hydrogen and the bromine are going to go on to bromine. We can only have one bond to hydrogen, right? This is an acid-base reaction. What's functioning as the base? You only got two choices, the alkene or the HBr. Which one's the base? The alkene. Its pair of electrons, it's an electron pair donor to HBr. This is a base, this is an acid. And so the hydrogen's going to go to which carbon? Carbon number 1 or carbon number 2? Carbon number 1. So I'm just going to draw that one hydrogen and there's two others there. What happens to this carbon when I take this pi bond? What happens to it?
It wants to form a new bond.
It does, but why? I'm missing something there. I've got carbon with 3 bonds. What does carbon like to have? 4. So what's its formal charge? +1. It's a carbocation. And of course we have bromide, Br minus. That's what happens in the first step. This is an intermediate. Okay? This is unstable. Carbon wants to have 4 bonds. So what happens? So the bromide, right, does what? How do I draw the arrow? Where do I start from? Which one has the electrons? Bromide, right? And that's the product. Okay, that's the mechanism for the addition of HBr across a carbon-carbon double bond. Okay? So, that was some review from last time. Let's see if we can get through the stuff we need to get through today. The other thing that we can add across a carbon-carbon double bond, bless you, is we can add halogens across the carbon-carbon double bond. Okay, we can add what they call X2 here. All right? So, we can take our alkene, we can react it with bromine, for example, or chlorine, doesn't matter which one. I'm just going to pick on bromine. And I can get what's called a vicinal dihalide. That is a vicinal dihalide. Vicinal meaning that the 2 halogens are on their adjacent carbons. Okay? This works for chlorine and bromine. You can take an alkene and bromine and do this. You can take an alkene and chlorine and do this. Iodine does not work. Iodine will add, but it comes back off again very quickly. Okay? For those of you who like high quality olive oil, this is exactly how they test for the virginity of olive oil. Okay, extra virgin, whatever you want to call it. All right? So they do what's called the bromine test. And they determine how much bromine the alkenes of the olive oil will take up. And the fresher the olive oil, the more bromine it will take up. Okay? It's called the bromine test. And it's simply this reaction. They're measuring how much bromine they can add to a given unit of olive oil. Olive oil is, a fatty acid, and it's got alkenes in it. And so you should be able to figure out the stoichiometry of that pretty easily, and that's how they test the purity, the virginity, whatever you want to call it, of these olive oils. Okay, it's through a thing called the bromine test. So, here's some examples, right? We're taking, how would you name that alkene? CH2CH2. What's the parent? You're close. It's not ethyl. It's ethene. That's right. This is ethene. So if you take ethene and chlorine, you get 1,2-dichloro. What's the product? 1,2-dichloroethane, right? So we're taking ethene, we're adding chlorine to it, and we're getting 1,2-dichloroethane. We can take this alkene, how would we name this one? No, not the product. The alkene. You're close. Getting ahead of us. Cyclohexene. We can add bromine to it, and now we get 1,2-dibromo cyclohexane. Right? That's right, because there's no double bonds anymore. So we can add these halogens across the double bond pretty conveniently. Okay? Turns out the mechanism for this is a little different than what we learned for. There is no carbocation intermediate in the addition of halogen, X2, to an alkene. Okay? What happens, got to kind of draw it out, is that you have one of the pair of electrons attacking bromine, and bromine can get attacked here. Why is that? Why is it okay here? I told you it couldn't happen the other time, right?
There's no dipole in this.
There's not much of a dipole at all, right? But there is an electronegative atom attached to it, so it can still accept electrons. But one of the pairs of electrons also comes back and forms a bond with the other carbon. So you form what's called a bromonium ion intermediate. A bromonium ion intermediate. Okay? You think that's stable? Why not? Why isn't that stable? It exists, so why isn't it stable? If you're bromine and you're electronegative and you want to pull electrons to yourself, do you think you're going to be happy being positively charged? No, you're not. Halogens don't like to be positively charged. They can be, but they don't like it, right? For obvious reasons. They want to attract electrons to themselves, okay? Now, the bromide comes in and attacks one of the carbons, and you end up forming the dihalide. Okay? So that makes sense because this ring is pretty strained. Right? So let's imagine for a second that this is bromine. And I'm going to make it into a bromonium ion intermediate. Look at my bonds, right? They're strained. They're under a lot of tension, if you will. So it's pretty easy for a nucleophile to come in and attack that carbon and break, well, I completely broke it, break that bond, okay? Three-membered rings are what we call strained rings. Okay? And you can see that when you try to build your model. This is a strained ring system, and so it will undergo reaction pretty readily, okay? Why does this form, you might ask? Why would a bromine that doesn't want to be positively charged be positively charged? Because everything here has an octet. The carbocation intermediate does not have an octet. Okay? And we know that carbon always wants to have an octet if it can. And so it forms this highly reactive intermediate that will eventually react and form other things. Okay? So that's what's going on. All right? So I want you all to get together in your groups for about, let's make it 4 minutes. And I want you to work through those two problems. Tell me what you think those products are going to be. What about the first one? You okay? What do you think about the first one? What are we gonna make? You all know enough now you can name this? Well, how would you name it? Name the product for me.
1,2 bromocyclopentane.
1,2-bromocyclopentane. Close. Really close. What did she miss? Dibromo. That's right. You missed the di, right? 1,2-dibromocyclopentane. That is what we're going to make. Let's walk through the mechanism. So what's the first step going to be? What's the first thing that we're going to form? Well, we are going to add 1 bromo. There's going to be 1 bromine added in the first step. That is true. But what does that look like? It's not going to be cyclopentane yet.
Break the pi bond.
Break the pi
And then
bond.
donate to the bromine.
To one of the bromines, yeah. And then what it forms there? Do I form a carbocation or not? I do not, right? So I form what? What did we call that?
Highly reactive intermediate.
It is a highly reactive strained ring intermediate. We call that a bromonium ion, right? So that's the first thing that's going to form in this reaction. And if I build that out with my model, here's my 5-membered ring. I'm going to use this red atom again as my bromine. This is going to be the bromonium ion that I form in doing this. And I am playing all kinds of heck on my model kit. Things I sacrifice for you. And we got another bromide, right? So this is what I've just made. So, come on, pop on there. There we go. So I've got this, and I've got this, right? As I'm holding this like this, what is different about my model kit model versus what I've drawn on the board? What's different? Pardon?
The bromine is closer.
Okay, true. What else?
It's axial.
I heard something.
It's closed.
It's closed? What do you mean it's closed?
I don't know, you usually say that it's closed. The ring, the strained ring.
Okay. What else? All this is drawn in the plane of the board, isn't it? What can you tell me about what I have here?
It's 3-dimensional.
It's 3-dimensional. Where's the bromine? It's coming out towards you, isn't it? These 5 atoms more or less are lying in the plane of the board because of this ring that forces them to be planar. But this is coming away from me, or well, actually towards me, right? Sorry about that. Does that matter? Think that matters? Okay, let's see if it matters. So now I've got this bromide, right? And it's going to attack one of these carbons, right? So it's going to attack one of the carbons. It doesn't matter which one, they're the same. And I'm going to form the 1,2-dibromocyclopentane. I think somebody gave me that earlier, right? So if this is going to attack this model, how's it going to do it? This bromide is going to attack one of these carbons. Is it going to attack the carbon from the front? Or is it going to attack the carbon from the back? I'm seeing people mouth back, but you're not very confident. Why? That's right. Why will it attack from the back and not from the front?
Because they want to be as far apart from each other as they can,
Why?
because of their charges.
Well, this is negatively charged and this is positively charged. One might argue that they would want to be coming together like this, right? What does this atom need to actually attack, though? Does it need to attack the bromine or does it need to attack the carbon? It needs to attack the carbon, right? And if you look at it, if I tried to get to the carbon here, I'd interact with this bromine, right? My electron pairs would start to interact. But coming in from the back, I have no such interaction, right? So when the bromide comes in from the back and attacks this carbon, What does it do to this bond? Breaks it and forms a bond here, right? I've really got this all messed up. There we go. What can you tell me about these halogens now, these two bromines? If I flatten this out as a plane, what can you tell me about them? They're what? They are trans to one another. That's right. We're on opposite sides of the plane. Right? So is this accurate? Is that an accurate drawing? No. So if I'm looking at that, I've got one bromine coming out towards me and the other bromine is going where? Away from me. And so the way that we represent that in organic chemistry, something that's coming towards me, we represent with a solid wedge. And something that is going away from me, we represent with a dashed wedge. And so this is the only thing you form, is this trans relationship of these two bromines. So it is no longer appropriate for me to just call it 1,2-dibromo cyclopentane. What do I need to call it? Trans. Trans 1,2-dibromo cyclopentane. That is what I need to name this, because it matters. I could also theoretically have cis, but not in this reaction. This reaction only gives me trans because it goes through that three-membered bridged intermediate, if you will, the highly reactive bridged intermediate. Okay?
You said the solid wedge is.
Solid wedge is coming towards you. So as I'm holding it, this one is the solid wedge. It's coming towards me. This one is going away from me. So that's the dashed wedge. Okay, we're starting to talk a little bit about stereochemistry, how things are in 3 dimensions. Okay? It's no longer appropriate just to draw it with the single bonds like we've done. And in fact, what I would do is I would have, to be absolutely accurate, I would have said that the bromonium ion intermediate should have been drawn like that as well, from what I had in the model. Okay? Does that make sense? So solid wedges mean something is coming toward me. Dashed wedges mean it is going away from me, right? And these other atoms are lying in the plane of the board, right? So that's how we're doing it. This is how you need to be working problems in your homework when you're dealing with this kind of stuff. Draw it out, but build models and use the two to actually help you understand what is going on. It takes time. I admit it, but time well spent, okay? So it'll give you a better understanding of what's going on, because these things can actually model reasonably well the 3-dimensionality of what's going on. What about the second problem?
34-dichlorohexane.
1, 2, 3, 4, 5, 6. And so you're suggesting that we would have something like that. And then if I number 1, 2, 3, 1, 2, 3, yes. Okay. Very good. All right. Try that one on your own. Don't get in your groups. Just try that one on your own. Ah, there we go. Much nicer. So nice. In fact, I think I'll keep it. How would we name that? we'd start by finding the parent chain. What's the parent chain? How many carbons are in the longest chain? There are 4. 1, 2, 3, 4, right? So we'd circle that, right? So what's the parent? What's 4?
Butane.
If it were an alkane, yes, butane, but this is an alkene, so it's butene, right? It's going to be a 1-butene because we're going to start our numbering here, right? We always want to give the lowest number to our alkene. So now what do we have? We have dimethyls on what carbon? So this is 3,3 dimethyl 1-butene. That is correct. So we're taking 3,3 dimethyl 1-butene and we're going to react that with bromine. Right? What's the product?
1, 2, bromo, or,
Uh-huh.
yeah, 1, 2, di, bromo, 3, 3, dimethyl, butene.
Not butene anymore. Why not?
Oh,
Butane. Right. Yeah, you're right. So that's the product that we're going to get. Right? We're going to get that product. Okay? All we've done is add bromine across the carbon-carbon double bond. And we went from the 3,3-dimethyl 1-butene to 1,2-dibromo 3,3-dimethyl butane. Okay?
can you explain one more time why it goes from alkene to an alkane?
Because it no longer has the carbon-carbon double bond, right? So when we go from here, the functional groups are alkyl halides, but there's no double bond, so it's an alkyl halide at this point, or dihalide to be more specific. Now try this. Try this one on your own. Take that particular alkene, same alkene that we had before. Now imagine throwing it in water with a little bit of sulfuric acid. What do you think happens here? What do you think the product's going to be? Don't worry about naming it. We haven't talked about naming alcohols yet. But what do you think is going to happen? Pardon? And where do you think the OH is going to be? On carbon number 1 of the alkene or carbon number 2? I see 2. Heard 1. Why would you predict 2?
Because of the hydrogen.
Whose rule?
Mark.
Yeah, Mark. Close enough. You're good enough. Yeah, Markovnikov's rule, right? Markovnikov's rule is going to dictate that the hydrogen goes to the carbon with the most hydrogens. So you would predict that you would end up with the OH group, or the alcohol functional group on carbon number 2. Okay? That seems reasonable, right? That's the product you get. What's different about that and what you predicted? And you all predicted exactly what I expected you to predict. So don't feel bad about that. What's different? The shape is certainly different. Okay? Let's expand upon that. What do you mean by the shape is different?
The double bond is gone.
Okay, the double bond is gone, but it was gone in the top one too, right? Yeah. Okay, so we're doing an addition, but something else happened here, right?
The angles changed.
The angles changed. Okay, that's fair enough. What else?
We added a line.
Pardon?
We added a line.
I added a line. You're on the right track. Where did I add a line?
To two.
Did I change the number of carbons? Adding a line would suggest that I added a carbon somehow. Did I really add? I didn't add the number of carbons. I didn't add any carbons, right? But you're getting at the right point. They're connected differently, right? If you notice up here in the top example, all of the carbons are still connected exactly the same. We just got rid of the double bond, right? But if you look down here, this carbon, that carbon right there, is what kind of carbon? Is it primary, secondary, tertiary, or quaternary? Quaternary. It has no hydrogens on it. Do I have any quaternary hydrogen or carbons anymore in the product? I do not. Right? A carbon atom has moved. This is called a rearrangement. This is the bane of organic chemistry. Right? Carbon can rearrange and move and make new things, and it's really, really wonderful, but it can really be a pain in the rump, too. I was a postdoc at Vanderbilt doing my work, and we recognized that something was undergoing a rearrangement. It took me 2 weeks to figure out that that's what was going on. It was not doing what I had predicted it should have done. And it did, and it rearranged and made something else because it went through a carbocation intermediate that I didn't expect. Okay? That's what's happening here. Carbocations are highly reactive and they will rearrange to form more stable carbocations. So let's look at that. So, let's look at the mechanism. This is why mechanisms are so important, because just based on what you know, you would have predicted a different product, right? Now, anytime I have water and sulfuric acid, I always think of that as H plus HSO4 minus and water. Okay, it's just easier for me to think of it that way. Okay? The first step of this reaction is going to be an acid-base reaction. The alkene is going to react with the proton, the H plus. Lewis base, Lewis acid. Markovnikov's rule is going to tell me that that hydrogen has to go to carbon number 1. Okay? So let's draw that out. There's that hydrogen. This carbon, carbon number 2, becomes my carbocation. And I've got HSO4 minus and water around. Okay? Carbocations are reactive. They don't have an octet. They want to be more stable. And it turns out the more substituents you have attached to a carbocation, the more stable it is. What kind of carbon is this? Primary, secondary, tertiary? It is secondary. And it turns out that secondary carbocations are okay, but they're not as stable as tertiary carbocations. Well, what happens is one of these methyl groups shifts. So the electrons between that carbon-carbon bond form a new carbon-carbon bond. So 1, 2, 3, 4, 4, 5, and 6. So the 3-5 bond moves over to make a 2-3 bond. So you end up with that carbocation. And when we do a rearrangement, I like to use a little curlicue arrow. That's not a standard way to do it, but most people do it that way. So we've rearranged. We've moved carbon number 5 from being bound to carbon number 3 to now being bound to carbon number. So I'll just draw it out here. CH3. Okay. And now what kind of carbocation do I have? Is that primary, secondary, or tertiary? It is tertiary. You all need to know that tertiary carbocations are much more stable than secondary, are much more stable than primary. In fact, we say that primary carbocations for all practical purposes can exist. It's not technically true. Somebody got a Nobel Prize for making that happen, but you have to use a solution called magic acid. And as you can imagine, it doesn't sit around on everybody's benches for very long, okay? So it's highly reactive stuff. So now we've got that, water simply comes in and attacks here, and that's how you get the alcohol. We'll talk more about the other steps of the mechanism later in terms of the alcohol formation. But this is carbocation rearrangements. This can get extraordinarily complicated really fast. You can have hydrogen atoms that move to give more stable carbocations. You can have methyl groups or other alkyl groups move to give more stable carbocations. You can have rings that go from smaller rings to bigger rings to give more stable carbocations. The good news for you all is this is Chemistry 251, which is a survey of this, not a deep dive. There are entire graduate courses devoted to nothing more than carbocation chemistry. You're not going to get that deep. We're going to talk about simple little movements of either a hydrogen atom or some alkyl group. We're going to keep it pretty simple, okay? So this is an example of what we would call a 1,2 alkyl shift. It's moving from, well, this really in carbon 1 as we numbered it, but it's moving from the carbon here, which you could say 1 and then 2. So that's how you get this so-called 1,2 shift. These are carbocation rearrangements, and they can get really nasty really quick. You have some carbocation rearrangement type problems in your suggested homework. I will work some examples and video it and put it on as supplementary material for you to watch. Okay? I can't devote 3 lectures to carbocation rearrangements. Okay? And I don't expect you to know them in that detail. But you do need to know something about it. Okay? So the thing is, the rule that I always say, the cardinal rule of carbocations, when you draw a carbocation, ask you stop. Just stop right there and say, can it rearrange to a more stable carbocation? If the answer to that question is yes, do it. You will not hear me be that definitive about most things in chemistry. But it's true. If you draw a carbocation, you should stop, think, and say, can that rearrange to a more stable carbocation? If the answer is yes, do it. That is what I call the cardinal rule of carbocation chemistry. All right. We also learned during that first lecture last, whenever it was, last time we met, which I think was the 16th, maybe? I forget the dates. Last time we talked about chapter 5. We talked about the fact that there are 2 ways to add water across a carbon-carbon double bond. We can do it through, and let me just use a generic carbon-carbon double bond like they've done, right? We can react it with water and sulfuric acid. And we can make this type of an alcohol, right? But there was another way that we talked about, and it's a 2-step reaction called the hydroboration oxidation sequence, okay? In the first step, you react your alkene with a solution that's called BH3, borane. It doesn't really exist as BH3, but it's good enough, okay? BH3. You are adding a hydrogen and a boron atom across the carbon-carbon double bond. Okay? You are adding a hydrogen and a boron across the carbon-carbon double bond in that first step. In the second step, you are oxidizing off the boron and replacing it with oxygen. And that step is complicated, and we're not going to get into the mechanism of it. Okay? But it's called the hydroboration oxidation sequence. And what you should be asking me at this point is, why is he feeding me this when all we need is one reaction to make an alcohol? There is a reason why you need another reaction to make an alcohol, right? So if we look at another example, Well, this is how the solution of BH3 really exists. You buy it as a so-called THF complex, where they take borane, which is a gas, by the way. They bubble it into tetrahydrofuran, which is an ether, and you get this so-called BH3.THF complex. But it behaves like BH3, so I always just call it BH3. Okay? But you can buy it, it's in a bottle. Nobel Prizes were given for this. What was his name? I forget his name, that's too bad. Anyway, he's been gone for a long time now, but he was awarded a Nobel Prize for a lot of borane chemistry. Borane chemistry tends to be fairly inexpensive to do because the government at one point subsidized boron production. At one time, the stealth fighter was going to be powered by borane. I'll give you a little history here. So the government spent a lot of money in building up infrastructure for borane production. Turns out that they ended up not doing that because it gives a green flame. You can see it. Not very stealthy when you can see it, right? So all you needed was a green-seeking missile and you could hit the plane. If you could have a green-seeking missile. Because boron burns with a green flame. What happens in this particular reaction is kind of similar to what happens when you react an alkene with bromine, right? You end up with this type of a mechanism where the boron and the hydrogen are being added at the same time. The hydrogen and the boron are being added in what's called syn addition. They occur from the same face of the alkene. They're not trans. The hydrogen and the boron are actually on the same side. That's why we get the term syn addition. And then in the reaction, so let's take an example here where we have our propene. We add BH3. Notice you only get one product. Where is the boron going? Which carbon of the alkene? Well, if I number the alkene, right? 1, 2, 3, right? Which carbon gets the boron? 1, which has the most hydrogens. Oh, wait a second. This isn't Markovnikov's rule, is it? The hydrogen's not going to the carbon with the most hydrogens. It's going to the carbon with the least hydrogens. So this is an anti-Markovnikov addition of BH, or boron and hydrogen across a carbon-carbon double bond. That's how that works. It's the only product you get. And so when you then put it under the conditions to oxidize it, you end up putting the alcohol where the boron was exactly. So let's look at the example that they used. If I use water and sulfuric acid, catalytic amount, I'm going to get this product, where the OH is on carbon number 2. The hydrogen is on carbon number 1, right? But if I do this process, BH3 followed by hydrogen peroxide and base, to be sodium hydroxide, we usually just draw hydroxide, okay? I end up with this alcohol. Why is that important? Why do I need 2 tools in my toolbox to make an alcohol?
Because the structures are different.
The structures are different. If I want to put the alcohol group on the most substituted carbon, I'm going to do this and get the product. If I want to put the alcohol on the least substituted carbon, I've got to use this 2-step process called hydroboration oxidation. There are literally probably close to 1,000 different ways to make an alcohol. You're going to learn only 2 of them. The water that's acid catalyzed addition and the hydroboration oxidation sequence. Okay? This route, what's the intermediate here? What kind of intermediate do I form in the formation of this alcohol? through a carbocation intermediate. If I go back, is there ever a carbocation intermediate in that step? Does anybody see a carbon with a positive charge? No. There is no carbocation intermediate. So what does that tell me? If I do this, I got to worry about what?
Restructuring it so to become more.
I have to worry about rearrangements. This one didn't rearrange, it couldn't rearrange, but I have to worry about it. Do I have to worry about rearrangements if I do this? No. There are no rearrangements. Okay? Very important. So, the hydroboration oxidation sequence gives me what? Markovnikov alcohols or anti-Markovnikov alcohols? Anti-Markovnikov alcohols. That is, they put the OH on the least substituted carbon. Acid catalyzed hydration reactions give me Markovnikov or anti-Markovnikov? Markovnikov. And I have to worry about what? Carbocation rearrangements. Do I have to worry about carbocation rearrangements in the hydroboration oxidation? No, I do not. Okay? Very good. All right. So, I want you all, for the next 10 minutes, to break up into groups.
I don't have an answer for that.
Yep, me neither. And I want you to work out that little roadmap. You're going to take this alkene, you're going to add bromine across the carbon-carbon double bond, you're going to do acid catalyzed hydration, you're going to do hydroboration oxidation, and you're going to add HCl. Show me what you come up with.
Do we need to draw out the intermediates too, or is that something?
We're going to focus on the products, but to get to the right products, you're going to need to draw out the mechanisms. So get together and discuss with your colleagues. Group up. Heads across the carbon-carbon double bond, right?
Okay, yeah.
So where's your carbon-carbon double bond?
It wasn't there.
So the bromines are gonna head across those two. So these are the carbon-carbon double bond, right? That's where your bromine's gonna head across. So you got just 1, 2, 3. So you got 1, 2. This is right here. This is just a constituent on the alkene. This is the alkene. Yeah. Now you gotta think about those, how the bromines are with respect to one another. All right. Let's work through these together. So one of the things that you always need to do when you're talking about addition chemistry to alkenes is identify the carbons of the alkene first. It's going to be these, 1, 2. Carbon 1, carbon 2, right? So I know this is where all the chemistry is going to start at least, right? So in the first one going up, we're reacting that with bromine. So I'm going to make a 1, 2 dibromo, whatever, right? So we got to draw that out. So I know that the bromines are going to go across this carbon-carbon double bond. But how are the bromines going to be oriented? Are they going to be on the same side, on opposite sides? They're going to be on opposite sides, right? So you're going to draw one of the bromines coming out. It doesn't matter which one. The other bromine has to be going back, right? And what do I do with my methyl group, the CH3 here? It stays there. That's right. And I'm going to draw it going back. Yep.
If you had drawn from the bottom as towards you,
Uh-huh.
would that flip the orientation of the two on top?
That's how you would have drawn it if you'd made the other bromonium line. And both are correct. The bromines are trans to one another. Okay? So either one that you drew would be perfectly fine. We're adding water, catalytic sulfuric acid. What's the product going to be? What am I adding across the carbon-carbon double bond? An OH and a hydrogen. So we're adding water across the carbon-carbon double bond. Which carbon gets the hydrogen? Which carbon gets the OH?
One gets the OH, and two gets the hydrogen.
That's right. Notice I don't draw that with wedges and dashes. Why don't I? Because all of these carbons have other hydrogens on it. You can't have cis or trans. Okay? It doesn't exist in this case. So you don't have to draw it. Okay? That is a Markovnikov alcohol. What's the intermediate? A carbocation. So when you went through the mechanism, you should have thought about, can that carbocation rearrange to a more stable one? The first step is the generation. The hydrogen goes there. The carbocation goes there. That's a tertiary carbocation. Can that rearrange to a more stable carbocation? Theoretically, it could rearrange, but it would rearrange to a less stable carbocation. So if this hydrogen moved here and put a carbocation there, that would be primary. That's no good. If one of these hydrogens moved over here and put the carbocation there, that would be a secondary carbocation. That's not any better. That's not better than a tertiary. So it turns out that that's the carbocation that you go through. Okay? HCl. What's the product going to be?
One gets the CL.
Very good. And then our favorite hydroboration, oxidation sequence. What do we get?
One gets the OH, and two gets the H.
If I did that, I end up with this. That's the same thing as that, right? Do I end up with the same thing? I don't, right? It's exactly the opposite, right? So what happens is, I get that. Right? So this is a Markovnikov alcohol. This is an anti-Markovnikov alcohol. Okay. You all need to, when you're working problems, you need to build these roadmaps for the types of reactions that alkenes are undergoing. It's very important. You can look at this and you can understand the various things that you can do to an alkene. Look what we can do to an alkene. I can make alkyl chlorides. I can make a Markovnikov alcohol. I can make an anti-Markovnikov alcohol. I can make a dibromide. I can do a lot of chemistry with an alkene. Okay? And that's the take-home message here. It's very, very important for you to keep that in mind. We're going to finish off with a couple of little things here, and then we'll pick this back up on Tuesday next week, and then get into chapter 6. So, why is this important for all of you? Many of you are in nutrition and dietetics. You all deal with fatty acids. These are things that you all will consume. It's olive oil, it's canola oil. Your cell membranes contain these things. It's what makes the lipid bilayer. You'll all learn about all this stuff in biochemistry. Okay? But these fatty acids, they're called fatty acids because you've got all of this carbon and a carboxylic acid. Okay? Now we can have a couple of different types of fatty acids. Actually, we have several types of fatty acids. Here's an example of oleic acid, and here's an example of what's called stearic acid. This one's called an unsaturated fatty acid because it has an alkene. The bottom one, stearic acid, is called a saturated fatty acid. Which one is healthier for you? Saturated or unsaturated? Unsaturated. And in fact, it's polyunsaturated fatty acids, PUFAs, as some people call them, that you really want to eat in your diet, right? It's the things you get from fish, like omega fatty acids. You've heard all this stuff, right? So there's all these fatty acids out. What's the difference between those two fatty acids? The double bond. That's it. The number of hydrogens is the only difference. They have the exact same number of carbons, right? So do you think I can convert oleic acid into stearic acid? You bet I can. What would I have to add across that carbon-carbon bond to do that? What do I need? What's the difference? What did we say the difference was? Hydrogen. Okay? The only difference is hydrogen. If you ever go to the store and buy, like Crisco, it is hydrogenated plant oils. They take unsaturated fatty acids and they hydrogenate them. They add hydrogen across the carbon-carbon double bond. Unsaturated fatty acids, typically at room temperature, are liquids. Saturateds are solids. Okay? That's what they do to make your Crisco. Okay? All we have to do is add hydrogen gas across the carbon-carbon double bond. However, if I take oleic acid and I put it in a flask with hydrogen gas, and I come back in a million years, I'll still have oleic acid and hydrogen gas. So what do I need to make the reaction go faster? I need a catalyst. All right, and it turns out that the catalysts in these reactions are very expensive. Okay? You use palladium, platinum, or nickel. Nickel's cheap, but palladium and platinum are very expensive. This is why they're cutting off catalytic converters these days to get the palladium and platinum out of them, because they're very, very expensive. Okay? We'll pick up with this on next Tuesday. I need you to do two things. On your way out, I need you to drop off your exam on the table with everything. And I also need you to turn in problem 4.17 from chapter 4.